Hello, this is a screencast for section 2.3 and 2.4. This part of the notes is on two different types of solids. The first one is on ionic solids. So 2.3 is a structure of ionic solids. So you want to be able to know what the structure is like, what makes it up, what the particles are like, what types of bonds are holding it together, and also what types of properties they have and why they have those properties. So we'll start off here. An ionic solid is another term for that is a salt, and there's lots of different types of salt. It can be any ionic compound, which would be any metal and a non-metal that go together, and their charges cancel out. So the most common one is just table salt, sodium chloride, but you also have magnesium fluoride. So there's lots of different combinations. Any metal with any non-metal will make an ionic solid. So what makes an ionic solid is that you have ions at the points of the lattice that describe the structure of the solid. The points of the lattice, or lattice points, you'll see that term now and again. Those are the points that make up the structure of the solid. And different types of solids have different types of lattice points. So for an ionic solid, the points that make up the lattice are just ions, charged particles. They're held together by ionic bonds, which is a strong Coulombic force between oppositely charged ions. So it's a fairly rigid structure because of that strong force that's holding those particles together. Remember, Coulombic forces, that term is coming up again here. That Coulombic forces are proportional to charge over distance, and you might want to record that again. So the higher the charge, or the higher the charge on those particles, and the closer they are together, the stronger the Coulombic force, so the stronger the ionic bond. So the strength of the ionic bond, which when you're talking about a solid, is also lattice energy. You can think of lattice energy as how much energy it'll take to break apart the bonds between the lattice points. So the strength of that lattice energy depends on the charge of the ions and the distance between the ions. So smaller ions will have shorter bond lengths, and that means that'll be a stronger bond. So shorter bonds are stronger bonds because they're Coulombic forces. Then the properties, they tend to be stable, have high melting points, brittle, they're non-conductive as solids, but they are conductive as a liquid, or they're aqueous. I'm going to come back to the properties after we get the structure of these ionic solids down. Okay, so these are the particle drawings. So the one on the left is a three-dimensional drawing. So you see the red circles, those are your sodium ions, and you see the chloride ions, those are your green circles. That's three-dimensional. You can draw that if you want, but if you're artistically challenged, I would go with this one on the right. Okay, and pay attention to details. You notice that the negative ions are larger than the positive ions. So you want to make sure you represent that in your drawing too. Negative ions are larger because they're gaining electrons to turn into an ion, so they expand a little bit, so they become larger. The sodium ion will lose an electron, so it loses its outside energy level, so they become smaller than their parent atom. So make sure you make the sodium ion smaller than the chloride ions. And you don't have to draw this entire thing. I would maybe have, you don't have to draw 16 of each ion. Maybe if you have just 9 of each ion, that shows you a good representation of what's going on. And just make sure you understand that it's positives surrounded by negatives surrounded by positives. Okay. And then like over here, the little line in between them, that represents the bond between the ions, or the lattice energy. Okay. So take a second and draw those out. You can pause the video if you need to. Okay, now I want to go back to the properties on the previous slide. Too far. There we go. Okay, so the properties now, and you want to understand why. So you might want to take some notes on this information here too. They're stable. They're stable because it's a strong Coulombic force holding them together. It takes a lot of energy to break them apart. Okay. They have high melting points for the same reason, because it's a relatively strong Coulombic force that holds the ions together. So you have to input a lot of energy, as in get it to a very high temperature to break those bonds. Okay, it's ionic bonds that have to be broken for an ionic solid to melt, and that generally takes a lot of energy, so it has to be at a high temperature, so they have a high melting point. Ionic solids tend to be brittle, as in if you hit them with something hard like a hammer, they tend to break apart. They don't give, they break. That's because of their structure. If we go back to a picture of their structure, take this one on the right, for example. Now, if you displace some of these ions, as in if you take a hammer and you hit this line of chloride ions, what will happen is that if they're all shifted down, then what happens is you get negative ions next to other negative ions, and positives next to positives. So in that case, they repel each other. So when you hit them with something hard, they tend to break apart because you have like charged ions that get next to each other. So if you disrupt this structure, it breaks apart. It doesn't give, or it doesn't bend. Okay, going back here, they're non-conductive or insulators, as in they don't conduct electricity as a solid. That means the electrons are not free to move. So in an ionic bond, those electrons are transferred from one ion to another. So they're not free to move around and conduct electricity. So that makes them insulators as a solid. But if you take an ionic solid and now you melt it, or you dissolve it in water, that's what aqueous means. Now you have charged particles that can move around, they can flow. That's able to then conduct electricity. So to be conductive, you need charged particles that can move. So in the solid form, they can't, but if you give them enough heat energy, then the ions can move around, or if they dissolve in water, then the ions are free to move around also, and that allows these ionic solids to then conduct electricity. Okay, now let's go to 2.4, the structure of metals and alloys. So with metallic solids, they're held together by metallic bonding, which is a special type of delocalized non-directional covalent bonding. This is also referred to as the electron C model. And you think of C as in something that can flow. Well, in this case, what's flowing is the valence electrons. They are free to move around. And that's what gives metals all of its properties. So let's go ahead and draw this particle diagram right here. Okay, you can pause the video if you need to. But once you're done here, then I can go through a couple things. So this is what a metallic solid looks like at the particle level. So the positively charged circles, those are metal ions, like iron positive 2, copper positive 1, whatever the metal happens to be. These little dots in between them are your valence electrons, okay? Just the electrons that would be on the outside of the atom, all right? These electrons are called delocalized. So if something's localized, that means it's stuck in one spot. But if something is delocalized, that means they don't belong to any particular ion, so they are free to move around. So these electrons are free flowing. They can move between any of these spots right here. So that's what gives metals their properties. So the properties are listed down here, and again, you might want to take some notes on why they have these properties. So metals tend to be good conductors. So to conduct electricity, you want charged particles that can move. So these electrons are free to move around, so that makes them very good conductors of electricity. They're malleable. Malleable means that if you hit it with something like a hammer, it will give, it won't break. So you can take metals and you can hammer them into really thin sheets, like gold foil or aluminum foil. You can kind of think of these the mobile electrons in here as kind of like a cushion between the metal ions. So if you hit a metal with, say, a hammer, it will give. It won't just break apart. So it's a hard structure, but it also has the ability to be pounded into a thin sheet. It's hard, but it's not a rigid structure. Rigid structures will break under pressure. That's not what metals are. Okay, metals tend to be hard, but not rigid. So you can hammer them into thin sheets because the electrons offers kind of a cushion between the metal ions. And ductile means you can pull them into a thin wire. So you can apply pressure to metals and they tend to not break because they're hard solids, but they're not rigid solids because of the sea of electrons. And they also have a wide range of hardness and melting points, and it depends on just the attraction between the metal ions and the electrons. So you get some metals will melt at really low temperatures, some at very high. So it varies from metal to metal. Okay, now a little bit more with metals. We have alloys. Those are mixtures of metals, and really most metals that you see and work with are alloys. You can mix together different elements together to make different metals. The way you mix them together is just you can heat them. So the heating gives the particles more energy and allows the particles to mix together. So properties of alloys are different than the original metals, and you can really construct these to have pretty much any property that you desire just by mixing together different types of atoms. When you add different things to these metals, when you mix different metals in, there's more attractive forces within the metal. So they tend to become a little bit more rigid, a little bit harder. Okay, so there's two types of alloys that you want to know about. And the first one is substitutional alloy. So with a substitutional alloy, that's where you're mixing together similar sized particles. So you take the pure metal right here, and then you would take some other atom that has a similar size, and you would heat them together, and the atoms will replace one of the original atoms that was in the structure. An example of that would be bronze, where it's a mixture of copper and tin, which both have similar sizes. The other type of alloy is called an interstitial alloy. That's where you have different sized particles. So if you take the pure metal, when you make an interstitial alloy, the smaller atoms will just kind of fit in the gaps between the original metal ions. All right. So you need different size particles for this to happen. A good example is carbon steel, where steel is mostly iron, and you can heat it together with some source of carbon, and those little carbon atoms will just fit in between the iron atoms, and it'll give the iron some different properties. All right, it makes, with these extra sources of attractive force, it'll make it a little bit more rigid, a little bit stronger, so it gives it some good properties to work with. So carbon steel is a good example of an interstitial alloy. Okay, and that's all for that section of notes. Have a great day.